In this video, we're going to be doing a rotations FRQ on a mass pulled by a string through a hole. So we're going to see how centripetal force motion is going to change with variable radius, and also why speed increases when our radius decreases. So we have a small mass is attached to the end of a string revolving in a circle on a frictionless tabletop. So let's draw our tabletop out. In a circle, we're going to have that our mass will be moving. So at a radius r is going to be where the mass will be connected. And we have our string, for example, would be pulled by our hand here. So initially the mass is going to revolve around with a speed of v1 is equal to 2.4 meters per second. In a circle of a radius r1 is equal to 0.80 meters. Then the string is pulled slowly through the hole so that the radius is reduced to r2 is equal to 0.48. So we are going to have a variable radius, and we're going to see how this is going to change. So in this situation, we are going to have no external torque because of the fact that our tension force is always going to be radially inward. So if it's always going to have a tension force that's in the center, this means that we have a centripetal force. Centripetal force just means that the summation of your forces is going to be making the circular motion continue. So our torque is equal to r cross of F, and since the force is going to be parallel to r, that means that the torque is going to equal to 0 because the cross of two parallel vectors is equal to 0. So either they're parallel, which means that they're going to be directly on top of each other if you were to align the vectors at an angle, or they're going to be anti-parallel and they're going to point in opposite directions. Now, if you have FR sine of theta, sine of 0 degrees is 0, so that's also how you see the torque is equal to 0. So if your external torque is going to be equal to 0, that means that L initial is equal to L final because your delta L is going to be conserved. Now for angular momentum, when we have a point mass in a circle, we are going to have that our angular momentum is I times omega. And for a point mass, when our mass is always going to be kept at a consistent radius, a consistent distance from the pivot moving in a circle, that's just going to be the mass of the object times the radius that it's being kept at squared. So then we can write our angular momentum as mr squared times omega. Next, we convert our angular velocity into linear velocity. We know that v is equal to r times omega, but we want to solve for omega, so we're dividing both sides by r, and we get that omega is going to be v over r. So we can take omega here, and then we can substitute that into our angular momentum. If we do that, then we get that L is going to be equal to mr squared times v over r. What you can do is you can cancel one of those r's, you're left with one r, you have L times mrv. So this is going to be one of our results. So if we again go back to our conservation of angular momentum over here, what we can do is we can plug in this expression onto both sides. Since we know L is equal to mrv, we can write that mr2 v2 is equal to mr1 v1, where the 1 and 2 are going to represent our initial and our final states. So after that, what we can see is we have the same mass on either side, so we keep the same mass, therefore we can cancel that out on both sides. What we want to solve is for our v2 in our problem. So to get v2, we would just divide both sides by r2, and then we simply get that v2 is equal to r1 times v1 over r2. All you would do is just plug in your values here. You'd have 0.80 for radius 1, and then for your v1 you had 2.4. For r2 you had 0.48, and this would give you 4.0 meters per second. So that is our v2. Therefore, we see that as our radius is going to decrease, our mass must increase its speed. It must move faster to keep our angular momentum L constant. That's why our v increases.